Hi, in later video, I given detailed introduction to density-based scanning algorithm, principal scanning algorithm. From this, uh, from this, I will give the detailed explanation. From this, I will give a detailed explanation uh, of density-based scanning algorithm. Okay, let's go. Density DBSCAN, which means density-based scanning algorithm. Everyone knows. DBSCAN estimates the density by counting the number of points in a fixed radius neighborhood and consider 2 points as connected if they lie within each other's neighborhood. A point is called core point if the neighborhood of the radius EPS contains as at least min points, that is, the density in the neighborhood has to exceed some threshold. A point Q is directly density reachable from a core point P if Q is within the EPS neighborhood of P and density reachability is given by the transitive closure of direct density reachability. 2 points Q, P and Q are called density connected if there is a third point 0 from which both P and Q are density reachable. A cluster is then set of density connected points, which is maximal with respect to density reachability. Noise is defined as the set of points in the database not belonging to any of its cluster. The task of density-based clustering is to find all clusters with respect to parameters, DPS and minimum points. Here, we mention MIN PTS is a given database. In the following, we provide more formal definition. The D set database of data points. The definition of density-based cluster assumes a distance function, distance P, Q, or pairs of points. The EPS neighborhoods of a point P denoted by NEPS of P is defined by NEPS of P is equal to Q equal D distance PQ greater than or equal to EPS. A point P is directly density reachable from a point Q with respect to EPS minimum points. P equal to N P of P NE PSQ and 2 NE PSQ greater than smaller than or equal to minimum points. In point P is density reachable from a point Q with respect to EPS and minimum points. If there is a chain of points P1, Pn, P1 equal to Q, Pn equal to P such that Pi plus 1 is directly density reachable from Pi. Density reachability is a canonical extension of direct density reachability. Since this relation is not transitive, another relation is introduced. Direct density reachability is canonical extension of direct density reachability. Since the relation is not transitive, but another relation is introduced. A point P is density connected to a point Q with respect to EPS and the minimum points. If there is a point O such that the both P and Q are density reachable from O with respect to EPS and minimum points. This concept, while P is density reachable from Q. Q is not density reachable from P. A and C are density connected via B. Intuitively, a density-based cluster is a maximum set of density connected points. Formally, a cluster C with respect to EPS and minimum points is a non-empty subset of D, satisfying the following two conditions in the upcoming slides. One, P, P and Q, P and Q. If P common Q is PC and Q is density reachable from P with respect to EPS and minimum points, then QC maximus maximality. You will see the diagram here. The similarities and dissimilarities between P and Q and then minimum points. In EPS and then minimum points. All of PQ with C, P is density connected to Q with respect to EPS and minimum points. Minimum points connectivity. Let C1 CK be the cluster of database D with respect to EPS and minimum points, then the noise is defined as the set of points in D not belonging to any cluster CI. That is noise equal to P, DP, CI. Density-based clustering district uses three different types of set. Core points, points with a dense of neighborhood, NEPSP, minimum points, that is minimum points, border points, points that belong to a cluster, but those whose neighbor is not dense, and noise points, that is points which does not belong to any other cluster. Example, Q and B are core points and BP and C are PA and C are border points. Density-based clusters have two important properties that allow the efficient computation. Let P be a core point in D. Consider set O and set O of all points drawn from D, which are density reachable from P with respect to EP, EPS, and minimum points. This set 0 is O is cluster with respect to EPS and minimum points. Let C be a cluster in D. Each point is in C is density reachable from any of the core points of C, and therefore a cluster C contains exactly the points which are density reachable from any and arbitrary core points of C. Thus, a cluster C with respect to EPS and minimum points is uniquely determined by any of its core points. This is the foundation of DBSCAN algorithm. Next, to find DBSCAN, start with an arbitrary database P and retrieve all points density reachable from P with respect to EPS minimum points, performing a cluster with respect to EPS and minimum points. If P is not a core point, no points are density reachable from P, and DBSCAN assigns P and P to the noise and applies the same procedure to the next database point. If P is actually a border point of some cluster C, it will later be reached when collecting all points density reachable from some core points of C, and will then be reassigned to C. The algorithm determines when all points have been assigned to a cluster or to the noise. Standard DBSCAN implementation are based on a spatial index such as an R tree or X tree, which provides efficient support of region queries that retrieve the EPS neighborhood of a given point. In the worst case, DBSCAN performs one region query per database point. This leads to runtime complexity of n0 n long n for DBSCAN, where n denotes the number of database points. Unfortunately, Spatial indexes degenerates for high dimensional data. That is, the performance of region queries degenerates from O log n to 0 n, and the runtime complexity of DBSCAN becomes 0 n square. For such data, on the other hand, if a grid-based data structure is available that supports 0 n region queries, the runtime complexity of DBSCAN decreases to ON, not that runtime complexity of 0 n long n is considered to be scalable to large data sets. An incremental version of DBSCAN can further improve its efficiency in dynamic databases with insertion and deletion, shows that density devices clustering can be updated incrementally uh, without having run the DBSCAN algorithm updates of rerun the DBSCAN algorithm on the updates database. It examines which part of existing clustering is affected by an update of the database and presents algorithm for incremental updates of a clustering after insertion and deletion. Due to the local nature of density-based clusters, the portion of affected database objects tends to be small, which makes the incremental algorithm very efficient. Thank you.